Sonia, thank you very much for your kind introduction, and before all the information you gave us, I just had a look to my clock and I saw I should have started my presentation 1 hour ago. So hopefully we will do the program during the day now, but I will need about 45 minutes. Is it okay to take 40 minutes? Okay, 40 minutes, okay. I will try to do my best. Yeah, thank you very much to all of you from the Croatian Geotechnical Society to invite me again to give this special lecture today. It is not with respect to the main topic of the conference, to the earthquake, but there is a very close relationship to the earthquake here 3 years ago, because it was the fire brigades of my hometown who were among the first who came here to the region to assist and to help. And when they came back, they really told about the tragedy which happened here. So I wish all people here all the best to overcome. And the good thing is there is a stronghold in Europe, and we are united now in the European Union, and much more important that we are united as humans. And as we can see, that we try to help each other, and this is one of the most positive aspects here. So I was invited to give a presentation now on innovation and sustainable development, contributions and strategies from geotechnics to alleviate the global energy crisis. What is hidden behind this title? It is quite general, I would say, and I would like to start with the common visions of the United Nations, which were established on a summit already in 2015. And you can see here the 17 goals. I do not go into detail of that, which were adopted by all of the countries which are part of the United Nations. And what was the idea behind? To set a new universal standard for development which aims to ensure that no one is left behind. The targets and indicators behind the goals provide a benchmark for measuring processes. And geotechnical engineering can do a lot, but I would like to focus on only one today. It is goal number 7, affordable and clean energy. But what does it mean, affordable and clean energy? It is a big word, but what is behind it? If you have a look to the renewable energy sources we have in Europe, and especially to the targets we have already achieved, and this is the latest report on renewable energy in 2020 of the countries of the European Union, plus Norway and Iceland. And we can see here on the left-hand side now the part of the energy which comes from renewable energy. And maybe you cannot read it, but we see our countries, Croatia and Austria, are in the first row. So obviously we are really good. But what does it mean, renewable energy? And on the left-hand side, we can see here what counts today to renewable energy sources. It's electricity from hydropower, electricity and heat from solar power, from solid or liquid biomass and from biogas, electricity from wind power, onshore and offshore. And lately we have a lot of discussions if nuclear power is renewable energy sources. And I'm definitely not of this opinion. Electricity from hydrogen, having a look to the future, and heat and also electricity from geothermal energy. And if we make a kind of a benchmark with respect to the overall impact, we can clearly see that we have really some very positive renewable energy sources, like electricity from hydropower, especially reservoir power systems, but also run-off river hydro plants, which are not so good, but not too bad. Electricity and heat from solar power is quite positive, with all the disadvantages of the photovoltaic systems. But the rest is, from my point of view, and it is not my opinion, it is the opinion of the experts and not of the media. This is not what we hear every day in the newspapers, on TV and the social media. this is not really renewable energy sources. Biomass, biogas, wind power, nuclear power, that doesn't really contribute to the targets of the United Nations, and doesn't contribute to the targets of net to protect our environment. And it is not time to talk about this in detail, but I would like to give you one example to compare energy systems with respect to the emissions of fuels for heating of buildings. And what I would like to say in the beginning, heating here is only on site. That means a central heating of the building, which is affected, and only the direct emissions are seen here. That means life cycle is excluded. And now if you have a look to those energy systems which are mainly used in Central Europe, this is now wooden pellets, heating oil, gas, electricity, air source heat pumps, geothermal heat pumps, and geothermal heat pumps run with photovoltaic electricity. We can clearly see that both particulate matter, what we also call this fine dust, Finoprach, or whatever you can say it here, and on the other hand, our carbon emissions. That we see wooden pellets is disastrous. Heating oil is much better compared to that. Gas is better than heating oil, but not good enough. But the good news is that particulate matter is not contributing so much. And electricity very much depends now where it is produced. And there are two benchmarks. On the one hand, from my home country, Austria, this is quite good. So we can see here the emissions of carbon is in average about 100. And if you compare that, for instance, to Germany, in Germany it's about 4 times higher. And there is a simple explanation for that, because we're an alpine country, we have a lot of hydropower, as we can see. So more of 50% of our electricity is generated by hydropower. In Germany, more of 50% are generated by coal. And that makes a big difference, because coal you can more or less compare to wooden pellets. It's the same part of the emissions. So if you have a look now to the air source heat pump, it is also a bit tricky. I'm not a fan of air source heat pumps because it very much depends on the outside temperature. If it is cold, it is more or less electricity heating. So much better is the geothermal energy. And you can see here, depending on the COP, I will talk about this a little bit later, we have very low carbon emissions, and particulate matter emissions are almost zero. And if we run this system with the photovoltaic electricity, we have zero emissions systems. And what we also have to think about is where are these emissions generated? And from the first 3 energy systems, emissions are generated on site, in the building, near the building, wherever there is the heating. But with all the others, the site is emission free, and with respect to carbon, it doesn't matter. But especially with respect to particulate matter, which can cause health problems, definite health problems, there it is emission free. So it makes sense to have a closer look, especially to the right-hand side. That means the geothermal energy. I wouldn't like to talk about the unsolved environmental aspects with respect to the nuclear power and the wind power. There is no time for that. But we should have in mind that both have a real bad impact to the environment. Okay, coming to geothermal energy. In the beginning, I would like to show you a case history, which is my private one. This is my house. This is the house of my wife and myself, which was constructed in 1899 by one of the family members of my wife. And those time, the house was heated with coal and with coke, and the heating demand was about 63 megawatt hours. In 1984, so 85 years later, my father-in-law refurbished the house and changed the heating system to a gas heating, but there was no thermal refurbishment of the house, so the heating demand remained the same. And a couple of years ago, my wife and myself extended the house. Now the size is double before. And what we did was a thermal refurbishment and insulation. And we reduced the heating demand by the number of 2, now taking into account here the square meters of the house. But in total, it remained the same, but it is double of size. And what we did, we changed it to a ground source system combined with a solar plant. That means on the roof there is solar panels and a PV system, and in the ground 5 borehole heat exchangers, each with a length of almost 130 meters. And if you have a look now, what is needed is, from external energy is just the blue stains here. It's quite a little. The rest is a gift of nature. And if you have a look to the numbers, we can see that only 15% of the heating demand has to be covered by external energy, by electricity, and 85% is given by nature. So this makes a big impact, having a look now to the emissions. If we start here with the carbon emissions and we have a reference of 100%, that means about 24 tons in 1899 was reduced about by 50% by changing to the gas heating system, and now it is only about 2%, so we have a reduction of about 98% if we compare to the original heating system. And it is more impressive if you look to the particulate matter. We have a reference of about 8 kilograms per year, just in one house. Can you imagine what this means for the health? This is the reason why 100 and 200 years ago, cities and towns were black. Yeah, this is obviously not happening anymore. And the change to the gas heating, we can see, was already a reduction by 95%. So gas is not so bad as we hear every day. Yeah? So gas is definitely not the best, but it is better than many other energy systems. And now the change to the current system, we can see there is a reduction of 99.5%. And what we have to take into account, what I've already said before, it is emission-free on site. And now what does it mean in absolute numbers? Every person here sitting in the room breathes out about 1 ton of CO2, of carbon dioxide a year. About 1 ton is produced by everyone. And now we have a look, what do we produce in the house? Also about 1 ton, but not at the site. So you can imagine, if it works, that we change all our heating systems to such plants, then we really can do a lot for the nature, we can do a lot for the environment. Geothermal energy. This is one of the solutions I would like to talk about today. So geothermal energy is not new. If we have a look to our ancestors, they already benefited from the so-called thermodynamic inertia of the ground. They lived in caves. We have a lot of nice caves in Croatia. Here is a picture of adjacent Slovenia, Postojnska Jama. And what did the people do? They spent a lot of time in the caves, because in summer, when it was very hot outside, it was pleasantly cool inside, and in winter it was the other way around. It was pleasantly warm inside when it was very cold outside. And this is due to the so-called thermodynamic inertia. And exactly that we use today when we utilize geothermal energy. And what is necessary to utilize it? An invention which was already done in 1856 on experiments on the reproduction of heat bound in steam by water power for use in evaporating brine. And what did this guy, Peter Ritter von Rittinger, wanted to say? Nothing else, he invented the heat pump. Because with the heat pump we can increase the temperature, which is relatively low in the ground in average, between about 8 and 14 degrees, to temperatures which are needed for heating purposes. That means at least 25 to 35 degrees. And we have different systems today, the deep geothermal energy I will not talk about today, and the shallow geothermal energy, which I will talk about today. In Austria, there is a clear limit between deep and shallow. It is 300 meters, because it's due to the different rights which have to apply and different laws which have to apply. Up to 300 meters we have the water right, and beneath we have the mining right. So this is shallow geothermal energy. And there is one more question: do we have enough of geothermal energy? And we did a study already 15 years ago in Austria. You can see our country, Austria, with all the big cities, Vienna, Graz, Klagenfurt, Villach, Innsbruck, Salzburg, Linz, etc. And what we can see here, only in the centers there are some red spots. That means there is no coverage of demand, but we have to take into account, we investigated only up to depths of 100 meters, and we did not take into account the groundwater. So it is really just the earth we took into account, and only up to a depth of about 100 meters. And in the rest of the country you can see yellow and green spots, and that means that there is a distinct surplus and an excessive surplus. So if we talk in absolute number, we have in total in Central Europe, it is not only valid for Austria, it's also valid for Croatia and all the other countries, we have a surplus of about 1,000 to 10,000 times more energy which is available compared to that we need. So there is definitely enough geothermal energy for everyone. So having a look to the system, how do such systems work? Geothermal energy is a sustainable, renewable primary energy source, and it is supplied for heating and cooling if we take into account the shallow systems. And it consists mainly of two circuits, the primary circuit, then the secondary circuit, and in between the heat pump. And the primary circuit is made of a closed loop system or an open loop system. And from the geotechnical point of view, it is interesting to have a look how we can extract the energy out of the ground. And we have been working on that for almost 29 years now. Closed systems, piles, geotechnical elements, board piles or board pile groups are earth-coupled structures, as well as driven piles and walls made of diaphragm walls, board pile walls, mixed-in-place walls, sheet piles walls in the meanwhile, slabs, all the floor slabs can be used, tunnel elements, tunnel slabs as well, lining segments, and these so-called heat exchanger pipes are incorporated in concrete structures. But they're more, for instance, geotextiles and tunneling, or even anchors we developed, and others like sewers in big cities that transport a huge amount of heat which can be utilized. And deep geothermal energy, borehole heat exchangers, the open systems mainly are wells, shaft wells, drilled wells, and horizontal filter wells. And also energy can be generated from open water, from rivers, from lakes, ponds, etc. And others are, with respect to the deep geothermal energy, the hot dry rock technology and the hydrothermal doublet. And with these systems also electricity can be generated. And if you have a look to a typical metro station which were constructed in the last years in Vienna and which are also currently constructed, we can see that energy piles can be applied, but also energy board pile wall, a diaphragm wall, energy tunnel slabs and the energy floor slabs, and also the energy geotextile or lining elements can be used to generate the energy. So the positive thing is that we can use synergetic effects. Yeah, so all these elements need to be constructed anywhere for structural reasons, for static reasons, and we can at the same time use this element to generate the energy out of the ground. Sure, we need a place for the heat pump and the cooling machine, we need a place for all the pipelines, etc. And before we go a little bit more into detail of that, I would like to present now the advantages when we have a look to the operation schemes. So the main application is the heating with heat pump, high savings of primary energy, because if you have a coefficient of performance of 4, that means it is the usable energy divided by the external energy, that means the electricity, because both can be used. Then we have a coefficient of performance of 4 if, for instance, 25% of electricity is needed to run the system. Nowadays, I would say we have COPs of about 5 and even more. That means we need, in average, less than 20% or less than 20%. And typical elements are shallow thermal heat collectors or borehole heat exchangers or shaft and drilled wells, with the disadvantage that they have to be constructed separately compared to that what I have presented on the slide before. Direct heating without a heat pump, for instance, for prevention of ice formations at platforms, ramps, roads and bridges, can be done in some special cases, but at the same time more important is the cooling purpose, which is more and more increasing. Cooling with cooling machine, okay, it is the reversal process of the heat pump. Everyone has a fridge in our apartments, in our houses. This is exactly the same principle, but much more of interest is the direct cooling when no cooling machine is needed, because there is no need of any air conditioning machines, and only the energy for circulation pumps is necessary. And from my point of view, it is really impressive, and we've proven that in our house, where we also have a so-called ceiling cooling, that the removal of 50 kilowatt waste heat can be done with just 1 kilowatt of pump power only. And to give you the example of our house, so every year we have about 5,000 kilowatt hours we bring back to the ground to regenerate the ground with our borehole heat exchangers. That means we just need 100 kilowatt hours, and 100 kilowatt hours cost about 40 euros. That means the cooling of a house with including 5 apartments just costs 40 euros. And this is a big, big advantage, and we should much more focus on that. But in the respect of sustainability is when such plants are operated seasonally. That means the ground is used as a heat storage due to the thermodynamic inertia I've already mentioned before with respect to the caves of our ancestors. They did exactly the same. Giving an example here, in summer we start to cool the building. That means we heat up the ground. In autumn we have a heated up ground, and this heat can be used in winter for heating the building, so we cool down the ground again. And in summer we have a cool down ground in order to start the reverse process to cool the building and to heat up. And if you're in a balance, then the ground is just a storage, nothing else. Yeah, and this is a big, big advantage. Coming now to the heat exchangers a little bit in more detail. Some applications in building construction and also in tunneling, what we did in the last about 29 years. Here we can see some typical energy pile and energy diaphragm walls. The absorber pipes or heat exchanger pipes, as they're also called, are mounted here on the reinforcement cage or the energy floor slabs. That means here in the blinding layer, all the borehole heat exchange, the heat exchanger pipes are installed, and they can be combined with energy piles as it is shown here in the photo on the right-hand side. Then already you can see between 2000 and 2003 we developed the first so-called energy wells, closed loop systems, which are very close to the classic borehole heat exchangers. And the big advantage of such wells is that we really have synergetic effects. In infrastructure buildings, they are mostly needed to dewater the system for groundwater lowering, and at the same time these wells are not needed anymore after construction, but they can be used then as heat exchangers, very close to borehole heat exchangers. In tunneling, we have developed 3 different systems: the energy tunnel slab, the energy geotextile, and the energy anchor. And already it was about in 2000, we applied it to a tunnel, the 12-kilometer long Lanzer tunnel in Vienna, which connects the center of Vienna to the western outskirts. And we had 2 pilot projects there, and we applied the so-called non-woven geotextile as an energy geotextile. And for the other way of tunneling, we can also use the energy lining segments. Here, a prototype testing was done, and you can see a typical arrangement of the heat exchanger pipes. Yeah, but also anchors can be used to generate the geothermal energy. So we developed 2 different types. This one with a smaller diameter, this one with a larger diameter, with a so-called coaxial pipe, which is just introduced here to the anchor. And we performed almost 20 years ago, 16, 17 years ago, our first test fields, also within the project of the Lanzer tunnel and in Vienna. And we saw that we can generate a lot of energy. Here the anchors were applied to a slope, and a huge amount of the ground can be utilized. If you have the open tunneling, cut and cover tunneling, then we have exactly the same elements we use for building construction. That means energy piles, energy diaphragm walls, energy floor slabs, and energy wells. So exactly the same technology we have already seen. Some special applications are of real interest, for instance, energy sewers. As I already mentioned before, there is a huge amount of energy we litter every day. And we can utilize this energy within the house, the in-house solution, or what we did already 17 years ago, the first plant for Vienna, for the city of Vienna, that we applied a public sewer. And the very interesting findings was especially the extraction performance, because it's about 100 times higher compared to that what we get out of the ground, about 100 times higher. And the explanation is quite simple. If you have a look to the first project we realized in the last years, the annual average temperature is about 16 degrees or even higher, and every second new energy is transported, because everything what is in the channel is flowing. And where does this relatively high temperature come from? From the toilets, okay, this is not so high, but from the showers, from the bathtubs, from the sinks, dishwashers, etc. And this is the reason why we have an average temperature all over the year of about 16 degrees, and this is an average 5 degrees higher compared to ground temperature. And this was realized now for the headquarters of Wien Canal in Vienna. It 2 new buildings with 8,000 square meters of space and 240 workplaces, and the electric power consumption of about 102 kilowatt for heating and 98 kilowatt for cooling. So that's a lot. And just a length of only 185 meters of this sewer is sufficient to supply the whole building, both with heating and with cooling energy. So this is an interesting technology. The only question which arises is, whom does this energy belong to? We never had these discussions in Austria, but I know there are a lot of discussions in Germany, for instance. Yeah? But this will be a question also in the future. Okay, and one example for open loop systems. Open loop systems are quite simple systems. I just need 2 wells for extraction as a source and a sink, and I take out the water. And as we can see in the simple example, if you have a pumping rate of 10 liters per second and heating cooling temperature of plus minus 4 degrees Celsius, we can achieve a thermal power of approximately 170 kilowatt. It's extremely efficient, and at the same time, it is very cheap to produce such wells. Sure, the permission practice is a little bit different, especially the determination of the hydraulic and the thermal range of influence has to be done, because the water right is very strict in this respect, and this is okay. And that's the reason why some complicated coupled thermohydraulic calculations have to be done. I do not go into detail of that, but this has to be done. Coming to the case history I wanted to introduce to you. It is the campus of the new University of Business and Economy in Vienna, which was constructed about 10 to 15 years ago. And I remember well when the project manager came to me and said, we have committed to green building, but we have no idea what to do. You have open hands, you can do whatever we want. So this was a nice situation, and we were thinking about what to do, and finally, the simplest and easiest solution was just to use the groundwater of the 2nd and the 20th district, which are the districts between the river Danube and the Danube Canal here. And the thickness of the groundwater is only 4 to 7 meters. But this is more than enough, because up to 150 liters per second are pumped out. This is a huge amount. And with this amount, the whole energy demand, both for heating and cooling, can be covered. And maybe you will ask, is it really possible to pump out 150 liters per second? It's a huge amount. And we had a lucky situation that in the early 90s of the last century, the hydropower plant of Freudenau in Vienna was constructed, which with the consequence that an embankment dam had to be constructed here. I was a very young engineer then and was assistant of my predecessor, Professor Brandl. And otherwise, the whole 2nd and 20th district would be underwater, would be flooded. Yeah? And so all the time water needed to be pumped. And it was quite easy. It was just a contract between the runner of the hydropower plant and the university to supply the water which is needed. It's very simple. And if you count now what means 100 liters per second, just what does it mean for a minute? What does it mean for an hour? What does it mean for 24 hours? It's really a huge amount. And what can be covered here? You see the annual heating energy of about 2.5 million kilowatt hours, about the double for cooling, and the peak heating and peak cooling power is about 2,400 and more than 3,000 kilowatt. So this is a huge amount. But the system is operating now for more than 10 years, and it perfectly works. And what we also had to take into account were all the water rights which were existing there. Some applications or some details we have to think about, and some more projects I would like to present now in the last part of my presentation. So not only the elements, the energy elements like energy piles have to be taken into account, but all the connection pipes they must place for them, the distribution blocks, the manifolds to the heat pump. And the first project we were working on was in 1994. It was the Arts House in Bregenz in the most western part of our country. And it was necessary to have such a steep foundation, both consisting of piles and of diaphragm walls. And the speciality of this project was that there was not a normal heating and cooling system. It was the first project where the so-called thermoactive concrete ceilings and concrete walls were activated. That means the heating and cooling happens within the building. That means all the walls and all the ceilings are equipped. Another case history, this was my personal study. It was the first project in Europe, and moreover, I would say worldwide, where a retaining structure for slope stabilization was used. This is a rehabilitation center in Upper Austria, and nowadays the whole building is heated and cooled with energy piles which were necessary for the retaining structure. And I remember well when my successor, Professor Brandl, was asked to work on this project, but in geotechnical terms. And then the idea came up to use all these piles as energy piles. He asked me, it's up to you now. Yeah, this is now your job, and think about it if it is possible or not. And it is still working today. One question which came up in the last decades is now the load displacement behavior of energy piles, because we have a thermal loading on that. These discussions we had with a lot of colleagues, especially within Europe, but also abroad, motivated us to perform some energy pile tests with respect to the axial pile load investigations. And we equipped two piles, one in quaternary gravel, the other one in Miocene sediments. And we did some calculations, some numerical simulations before, what we always do. And then we equipped these two energy piles with a lot of monitoring systems like sister bars for axial strain measurements, chain extensometers for axial displacement measurements, strain gauges for the radial strain measurements, temperature gauges over the pile for temperature measurements, both within and around the test piles, and also in the surrounding elements. And what is always very important, that we have a so-called dead load as loading, because we have to measure our displacement of the pile, and it does only work if you have a dead load. And just to give you some exemplary results, we have here the two phases, a loading of 600 and 800 kilonewton, heating phase and cooling phase. And here is the temperature development, both for heating and for cooling, not going into detail of that. But the interesting thing is there are some deformations, and they are not so little. So we have a heave and we have settlements just due to the thermal loading, and it is about plus minus 3 millimeters. And we have the same also measured with the longitudinal strain gauges. But what does it mean now for the load displacement behavior of such an energy pile? We compared these energy piles with normal piles, which were constructed very similarly. And what we could see here, that the energy pile is on the upper limit in the quaternary gravels, and it is much better. It is much better in the soft soil ground conditions. And what is the explanation of that? There is not a deterioration. It becomes better because we have a kind of a thermal pre-stressing of the piles, yeah, which improves the performance of such pile with respect to the axial pile loading. Yeah, coming now to the last part of my presentation, very briefly. As already mentioned, we started about 28, 29 years ago to do the research in this field. And it was about 23, 24 years ago that we started with the two pilot projects I already mentioned in my presentation. And one is the so-called section Hadersdorf-Weidlingau, where we have an open cut. And on one side of the wall, 59 energy piles were equipped with this technology. That means every third pile was equipped as an energy pile. The energy performance was about 150 kilowatt, and this energy was used up until the last year for heating a school. I do not go into detail of this project, but a little bit more on this project, which was about the same time when due to the very positive results of our first pilot projects, the Vienna city decided to equip 4 metro stations with this technology, as we have seen as a schedule already in the beginning. So we did a feasibility study, instrumented and installed the energy diaphragm walls in this case, and also the energy bottom plate. And in 2008 we started with the monitoring, and we are doing the monitoring still now. And we did not only instrument the whole system, but we also had to solve a lot of different details like the connection points of the energy diaphragm wall, where to place them. For instance, you can see here the heat exchanger pipes lay out with 2 heat exchanger circuits. The connection points were below the bottom slab. Why was this necessary? Because we have a water pressure of about 25 to 30 meters. That means we needed a water pipe penetration through the bottom slab, which was a challenge, but finally it worked, and we could also solve these problems. So it was the details which are challenging, not the idea behind. The idea behind is quite simple. And what we did, we instrumented the diaphragm wall element, as we can see here, with combined temperature and strain sensors, with a chain extensometer with 7 segments and some temperature sensors outside. And just to give you a few about what we measured in the last more than 14 years. So first result, the temperatures in the diaphragm wall is above 0 degrees, and it is necessary that there is no freezing. The temperature curve is almost independent despite continuous operating time over more than 14 years. That means the system is definitely sustainable. And the temperature trend above the slab is almost independent of thermal operation. That means that the temperature mainly follows the outside temperature, the ambient temperature. And the temperature difference between inlet and outlet in this case is less than 1 degree. That means that we have still large thermal energy reserves. And with respect to the strain measurements, just to give you one result, that the strains, that means about 0.17 millimeters per meter, are very, very small, and they are much, much smaller compared what is caused by structural reasons. That means also in this respect that the system works. So coming to my conclusion, we applied this technology for infrastructure buildings now for far more than 25 years. And that means these geothermal systems have been proven for decades now. And numerous systems allowed application in a wide range of boundary conditions and construction methods. And the most important message is there is no case of damage known up to now. And we have instrumented some hundreds of kilometers of these elements, and it perfectly works. So what we are doing now, generating long-term measurement data, as I've briefly presented, to verify the analytical and the numerical models. We're just developing further to optimize the system for future projects. We're just doing some thermomechanical modeling of energy piles. This is a following project of our Excel pilot test projects, and we are currently developing planning tools for the holistic design of geothermal plants, which is not existing until now. And not to show off, I present this, but already in 2008, we won the highest award for engineering work in Austria, the State Award for Transportation, in the scope of sustainable infrastructure for the 21st century. And as you can imagine, since the war in the Ukraine began, every day the phone rings, every day I get email, because now people have realized this could be a part of the solution. And when I mentioned in the title of my presentation that we have an energy crisis, from my point of view, it is not true. We do not have an energy crisis. We do not have an energy supply crisis. So did you have any problem with the supply in the last year? Not really. Not in Austria, not in Croatia, not in the US, not in Lebanon, or wherever. Yeah? We didn't have. Yeah? And we didn't have a crisis with respect to the energy infrastructure. Sure, it can be improved. We have just a situation of an uncertainty of the people, which is made by media, which is made maybe by politicians, I'm not sure about this, and this made the prices finally so high. And this is now in the focus of interest to apply these technologies which are available nowadays. And coming back to that, what I mentioned in the beginning of my presentations, the United Nations Sustainable Development Goals, the common visions, and you can see I've rearranged now these 17 goals through the 5 Ps. With respect to people, the provision of material needs, to prosperity, to planetary integrity, and to political institution, peace, and partnership. And where can we as geotechnical engineers contribute? In every row. So at the universities, in the high schools, we can do a good education. Provision of material needs, clean water, that's what I've talked about today, affordable and clean energy, and also the reduction of energy need we can do. As I've presented before, only 15% of the energy which we need comes from external sources. The rest is a gift of nature. Is a gift of nature. We have to take that into account. And with respect to the planetary integrity, we have the climate action which is important, and the prosperity. Sure, we have the industry, we have innovation, we have infrastructure. And I remember well, and some of you also attended this conference in 2017. It was the 19th International Conference on Soil Mechanics and Geotechnical Engineering in Seoul in Korea. Janko and Milorad and many of you attended this conference. And Ban Ki-moon gave the opening speech, and he said, I strongly believe that geotechnical engineering is the key to solving natural and man-made disasters derived from conflicts between man and nature. And this is a very, very important saying he did, and it should motivate us to be more self-confident that we really, as geotechnical engineers, can contribute to make a better world with respect to green building, always developed under the guiding principle of sustainability. That's it. Thank you very much for your introduction. Hvala lijepa.